Hello, everyone. I'm excited to present our work, Multi-GAT, a graphical attention-based hierarchical multimodal representation learning approach for human activity recognitions. I'm MD Mofizul Islam, PhD student, University of Virginia. My co-author and advisor, Dr. Tariq Iqbal, Assistant Professor, University of Virginia. So before explaining our work, let's take a brief overview of what is the multimodal learning. As a human being, if we consider how we determine any event or object which is happening surrounding our environment, we generally use multisensory systems, for example, visual, auditory, or the somatosensory information to identify what is happening around us. So we want to replicate the same behavior in the robots, so that robots can utilize the multisensory systems like visuals, physical sensors, and other sensors to determine the event or objects. But there are some challenges which we need to address to effectively utilize the multisensory systems to determine, say, an event. So the first challenge is to how we can extract the salient modality specific features and how we can fuse those salient modality specific features to extract the complementary multimodal feature recognition. There are some approaches have been studies in the literature to effectively utilize the multisensory systems. Let's take a brief overview of some of the approaches. The first is the early multimodal fusion. So in early multimodal fusions, let's consider that we have three modalities: RGB, depth, and skeleton. So each of these modalities raw features without employing any modality specific feature representation approaches. This raw feature will be combined, and then it will be passed through a learning network to produce the multimodal feature, which is then used for the task learning, that means human activity recognitions. It is a very simple approach to combine the multimodal features, but the problem is that it cannot capture the modality specific feature complexity or characteristics, because each of these modalities has its own feature distribution. For example, the feature distribution of the RGB or the visual modalities that will not be similar to the skeleton or the physical sensor modalities. So to address this issue, the late multimodal fusion approach has been proposed. So in the late multimodal fusion approaches, each of these modality will be passed through a modality specific learning network, which is then produce the modality specific features. Then these modality specific features will be used for the task learning network and produce the activity recognition probabilities independently by using all of these modalities features separately. Then this output will be fused to produce the fused activity recognition probabilities. This approach can solve the early multimodal fusion approaches and extract the modality specific features, but this approach doesn't allow the intermodality interactions to produce the multimodal feature representation. To address this issue, intermediate multimodal feature representation approaches has been proposed, which allow the intermodality interactions and produce the multimodal feature embedding, which is then used for the task learning network. So this approach effectively allows the intermodal interactions and extract the multimodal features. But the problem is that it depends on how the modalities will be interact to each other, and it depends on the human designers, and it may be biased and may not effectively extract the multimodal features. So although there are some approaches have been proposed in the literature, but there are some challenges there are some challenges in the multimodal learning approach which we need to address to effectively extract the multimodal features. So for example, extracting and fusing the complementary multimodal features by extracting the intermodality relationships. And most importantly, the state-of-the-art work doesn't consider the noisy modality in designing the multimodal learning approaches, because the state-of-the-art work generally assume that there is a non-noisy modality data is involved both during the training and the testing time, but which is not a realistic assumption. So because in the real world deployments, the noisy modalities may be present in some of the modalities or in all the modalities. So we need to design the multimodal learning approaches in such a way that it can effectively extract the multimodal feature representation from noisy modalities also, or the missing modality. So to address this issue, we propose a graphical attention-based hierarchical multimodal representation learning approach for human activity recognitions, namely Multi-GAT. So our main contribution is a twofold. So we propose a multimodal mixture of expert model for extracting the salient modality-specific features. And then we also propose a novel multimodal graphical attention approach to capture the intermodality relationship for extracting the robust multimodal features. So let's take a brief overview of our proposed approaches. So in our proposed approaches, there is a module: unimodal feature encoder, and multimodal mixture of expert, and the cross graphical attention crosslet. So in the unimodal feature encoders, we sequentially employ the spatial feature encoder, temporal feature encoder, and the unimodal attention approaches to extract the modality specific features, salient feature. And these modality salient specific features will be used for the multimodal representation learning approaches. And we employ the unimodal feature encoders independently so that we can capture each of these modality feature complexity and characteristics separately. Although we extract the modality salient modality specific features, but it may not extract the modality specific features which may be used for the multimodal representation learning space. So we disentangle each of these unimodal features and create some expert feature objects, which will be then be filtered using a multimodal MU-GAT based on the by observing the other modalities. That means each of these modality will produce some feature objects, and it will observe the other modalities. That means what is the other modality can provide in the multimodal feature representation space. Then it will extract the salient multimodal salient unimodal feature from each of these modality independently. So then it recalibrate its modality specific features and produce the salient multiple modality specific features, which will then use for the cross graphical attention models to extract the complementary feature. So in the cross graphical attention approaches, each of these modality will interact to the other modalities and to recalibrate its own feature space. For example, let's consider that we have 4 modalities: RGB, depth, skeleton, and the physical sensor. So RGB will interact with the depth, skeleton, and the physical sensors to recalibrate the RGB's own feature space. And the depth, skeleton, and the physical sensor will do the same thing and recalibrate with its own feature space by observing the other modalities. In that way, then each of these modalities have the complementary feature representations by observing the other modalities. Then we fuse these recalibrated features and produce the multimodal feature embedding, which is then used for the task learning network. That means the human activity recognitions. So we conduct these experiments on 2 multimodal activity recognition data sets. One is the AMEC data set and another is the UTM head data set. So in the AMEC data set, we have 37 daily activities, which was performed by 20 subjects, and it has 7 modalities, which is include 4 viewpoints and some physical feature sensor. And it contains 37,000 video clips and 2 evaluation settings across subjects and cross sessions. UTM data sets contain 27 daily activities, which is performed by 8 subjects and contains 4 modalities, including RGB, depth, skeleton, and physical sensor. Then the data set size is 861, and the evaluation settings. So we follow the leave one subject out. So at first we try to evaluate that how generalized our proposed learning approach is. So for this reason, we conduct this experiment on the cross-subject evaluation settings in the AMEC dataset. It helps to evaluate our proposed approach that how much generalized it for the unseen subjects, which may be present in, which may not, for example, some subject which is present in the training time but may not be present in the testing time, which is the which we need in the real world deployment. And the experiment results suggest that our proposed approach outperform all of the state-of-the-art approaches. And for example, a Multi-GAT outperforms the recent state-of-the-art approach by 4%. We also conduct this experiment in the cross-session evaluation settings. So in the cross-session evaluation settings, our proposed approach also outperforms all of the other state-of-the-art approaches and achieve almost a 7% improvement. So in that, we also conduct the experiment of the UTM had leave one out cross-validation sessions, and our proposed approach suggests that the multi-GAT outperforms all of the previous approaches. And it is noticeable that previous approaches only considers the attention approach or fuse the multimodal information, but doesn't consider the intermodality relationship to extract the multimodal representation. And we believe that the cross-graphical attention approach helps our proposed approaches to effectively extract the multimodal features. We also conduct this experiment with several modality combinations, and in all of these modality combinations, our proposed multi-GAT achieves the improved performance. Most importantly, we conduct this experiment in the presence of noisy modalities, and we conduct this experiment in two evaluation settings. In the first evaluation settings, we introduce noise both in the training and testing time. In the second evaluation setting, we only introduce noise in the testing time. And in all of these evaluation settings, our proposed approach outperforms all of the previous approaches quite a good margins in the presence of a noise, which indicates that the effective deployment in the real world environment. We also conduct the evaluation studies to determine what is the impact of our proposed different learning modules, and it can be noticed that when we introduce the modality specific features and the cross-graphical attention approaches, it helps to improve the performance. So our proposed multimodal mixture of expert and the cross-graphical attention approaches is crucial to extract the complementary multimodal features. We also conduct some quality evaluation studies. For example, when we utilize the non-attention approaches, it may not extract the distinguishable features. For example, here is the feature multimodal feature representation is overlaid for the throw and the lance activities, which is quite distinguishable activities. But when we employ the unimodal attention approaches, it separates the feature space, but it may not effectively separate the features. But when we introduce the multi-GAT, it appropriately produces the well-spaced clustered representations. And when we also consider the other modalities, other activities, it can be easily noticeable that our proposed cross-graphical attention approaches produce the well-spaced distinguishable multimodal features. We also conduct this experiment or evaluation study on the confusion matrix, and it can be noticeable that when we introduce the modality-specific attention and the multimodal mixture of expert, it effectively reduces the errors. And then when we introduce the cross-graphical attention approaches, it also further improves the performance. And most importantly, when you use all of the modality-specific features, multimodal mixture of expert and the cross-graphical attention, it helps to improve the performance. So here is the summary of our contribution. So we develop a multimodal mixture of expert model to extract the modality specific salient features. Then we also introduce a cross-graphical attention approaches with extract the intermodality relationships to extract the robust multimodal representations. And we thoroughly investigate by varying the modalities and also in the presence of noisy environment, and our proposed approach outperforms all of the previous approaches. Thank you, everyone. If you have any questions, we welcome to attend our live sessions, live question and answer session. Thank you very much.